Alright, so welcome back, Lecture 12B. So let's play around with this. Let's look at some conversions to and from floating point notation. So I've drawn our template here, and this is in the text, by the way. All of this material is in the text in section 5.6, and here's a picture of what single precision floating point looks like. And there's examples. Here's double precision, and you can see it's just a bigger exponent, bigger fraction, 64 bits. And so there's some examples in here you can look at, and so on and so forth. But let's play with some specifics. So let's look at the number 3F200000. And let's say, what does this number represent? If this is a 32-bit single precision floating point number stored in IEEE 754 format, what floating point number does this correspond to? Well, write it out. So 0011, that's 3. 1111 is F. 0010 is 2. And then it's going to be a bunch of zeros. And I usually start from the left because the fraction tends to either repeat or repeat specifically with zeros. So our sign bit is a 0. And then we want to pull off 8 bits of exponents. So 1, 2, 3, 4, 5, 6, 7, 8. So this is the exponent. And the rest of this is the fraction. So sign bit is 0. That means we have a positive number. Our exponent is what? Well, if this was a 1, this would be 127. This least significant bit is a 0, so this is 126. You can add up the powers of 2 or use a calculator or whatever, but this number in binary, this 8-bit number, is 126. And our fraction is just what we see. It's 0.010, and then a bunch of zeros after that. So according to our formula, right, this is negative 1 to the 0, so it's positive. 1 plus the fraction is 1.01, and it gets multiplied by 2 raised to the exponent 126 minus 127, that's negative 1. Okay, so we have to convert this into decimal. So this is 1.01. Well, this is 1. This is the 0.5's place. This is the 0.25 place. So this is 1 plus 0.25, that's 1.25. And 2 to the negative 1 is 0.5. And so this is 1.25 divided by 2, which is 0.625. So this should be the floating point representation for the number 0.625. So we can actually check that if we don't mind playing around a little with some Unix. So I have a little program here called F for float, and it has a single line of code which says X is a floating point number and its value is 0.625. And I'm going to compile that. And that gives me an executable program X, right, or F. It doesn't do anything, right, it just assigns a value. But there's a function called XXD, which will let me look at the contents of this executable program F in hex, and will also print out printable characters over here. So here's my program, and it's got some code in it, it's got some tags to say it's an executable program and so on. But if I go down here around position 6A, and I look at these 32 bits, that's where it's storing the number 0.625, and you read it from right to left. So it's storing a 3F, a 20, 0000, and 3F 200000, that's the number we started with. That's our 0.625. So what happens if we wanted to store negative 0.625? Well, the only thing that's going to change is this sign bit. So we're going to store our negative 0.625. It's going to end up being 1 0, 1, 1, 1, 1, 1, 1, 0, 0, 1, 0, and then a bunch of zeros. And if we write that in hex, this first digit, instead of being a 3, is going to be a B. So BF200000 should correspond to negative 0.625. Well, let's check that out. So let's go back into f.c. Let's store x as negative 0.625. And let's go ahead and look at locations around 6A0 again. And 6A0, here's our number, and sure enough, it's BF200000, and that's what we calculated negative 0.625 should be. So this stuff really works, right? Your compiler, when you put in a floating point number, it goes through this process to convert it to a hex number, a binary number, and stores that inside the executable file. So this bit pattern is actually stored inside that program that you run, because eventually the CPU makes instructions that read these bits and interpret them as a floating point number, 0.625 or minus 0.625. All right, so let's keep going with this. So we took a hex number and we converted it into a floating point. Let's go the other direction. Let's take a floating point number, say 0.2, and convert it into this floating point notation. So 0.2, well, we want to represent it as something times 1 plus a fraction times a power of 2. And we want our fraction to be something that is bigger than or equal to 1. So 0.2 equals, we could write this as 0.1 times 2. No, let's not do that. 0.2, we could write it as 0.4 times 2 to the negative 1, which is 0.8 times 2 to the negative 2, which is 1.6 times 2 to the negative 3, which is 3.2 times 2 to the negative 4, and so on. To put our number into this floating point notation, we have to represent it as a power of 2 multiplied basically by 1 point something. Okay, something that in our binary coding is going to be a 1 followed by something. And so this is the way we want to represent it, 1.6 times 2 to the minus 3. If we represent it like this, it's going to be 1 point something. If we represent it like this, it's going to be 0 point something. So we're moving the radix point back and forth the same way we do with scientific notation to make sure there's a single digit to the left of the decimal point. Same thing here. We'll see another way to do this in a second, but 0.2 is the same as 1.6 times 2 to the negative 3. And so if we write our number in this form, it's pretty easy to translate it into this, right? So 1.6 times 2 to the negative 3, and it's positive. So s is going to be 0. Our fraction should be 0.6, and our exponent minus 127 should be negative 3. Okay, well, let's do the exponent first. Exponent minus 127 is negative 3, so our exponent is 127 minus 3, which is 124, which as an 8-bit number looks like this. So that's our exponent. And then our fraction should be 0.6. Well, how do we write 0.6 in binary? 0.6 times 2 equals 1.2. 0.2 times 2 equals 0.4. 0.4 times 2 equals 0.8. 0.8 times 2 equals 1.6. 0.6 times 2 equals 1.2, and we're off and running. And so we pick up these digits, the most significant digit starting at the top. And so this fraction equals 0.1001, 1001, 1001, and so on. All right. And our number is actually that plus 1, but we're not going to store that plus 1 because when we calculate the floating point number, it's 1 plus this fraction. So our complete storage of the number 0.2 should be a 0 for the sign bit, 0, 1, 1, 1, 1, 1, 0, 0 for the exponent, and then a bunch of 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, and so on. And again, start from the left. Don't assume that your pattern ends with 1, 0, 0, 1, okay? Because we don't know how many times this repeats before we fill up the fraction. So start from the left when you're trying to write this in hex. Break this up into groups of 4. So there's your first group, there's your second group, there's 0, 1, 0, 0, there's your third group, 1, 1, 0, 0 is your fourth, 1, 1, 0, 0, and so on. Alright, so this is the number 3, this is E, this is 4, this is C, 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 C. So 0.2 should look like 3E, 4C, CC, CC. That's the 32-bit pattern that corresponds to the number 0.2. So let's double check that. So we'll set x equal to 0.2. And we'll go up here and we'll look at locations around 6A. 6A just happens to be where it stores these. There's no inherent reason. And here's our number. And it looks like 3E, 4C, CC, CD. So pretty close. 3E, 4C, CCC. But this last digit is a D. Why is that? Well, if you were to write this out, the very end of it would be 1100. There's the C that we had, and this is bit position 0. But if we were to write one more bit, it would be a 1. It would be the beginning of the next C, right? Well, how do we round? Our rounding rules say if you're at least halfway to the next number, round up. Well, 1 is halfway to the next number, so because this is a 1, this bit actually gets rounded up to a 1. And so our last nibble in here is actually 1101, which is a D. So that's why that comes out to be a D instead of a C. Concept is exactly the same as the other places, right? It's just a rounding that happens at the end. So that's basically all there is to the floating point representation. So we can round, we can take a binary number, 32 bits, and convert it to floating point, or we can take a floating point number and go through this process and store it in floating point notation. If you don't want to do this stuff in the beginning, let me show you a different way to do this. The number 0.2, let's pick on that again. So 0.2 times 2 equals 0.4. 0.4 times 2 equals 0.8. 0.8 times 2 equals 1.6. 0.6 times 2 equals 1.2. 0.2 times 2 equals 0.4, and so on. So 0.2 equals 0.001100110011, right? So 0.2 equals 2 to the 0 times 0.00110011. And now we're just moving decimal points or radix points. If we move this over one spot, right, to double this, we have to decrease our exponent. So it's 2 to the minus 1 times 0.01100110011. We can move it again and bring this point over here. So it's 0.1100110011. And we can move this one more time and get 1.10011001, and so on. And now we have this in the form that's required. It's 1 plus a fraction, so this is the fraction that we're storing. right, which was what we just did a moment ago. So, so we'll play around with this in class and get some practice doing these kinds of conversions. You want to look at the book, read through that section in the book, and pay attention in particular to this business of extra notations. So we know single precision, double precision, again, is just a bigger fraction, larger exponent, different bias. But there are some particular formats that have very special meaning. For example, if the exponent is 0 and the fraction is 0, that represents the number 0. And that's important because the way that we've been using this, right, we cannot write 0 as some power of 2 times 1 plus a fraction, because 1 plus a fraction is always going to be at least 1, and a power of 2 is always going to be bigger than 0. And so there's no way that we can actually represent a 0 using this formula. So we have special rules for if the exponent is 0, fraction is 0, that's the number 0. We can also represent infinity. If the exponent is 255 and the fraction is 0, that corresponds to the number infinity. It can be positive or negative based on the sign bit. And we also have things that are not in numbers, so we can store something like if you try to take the square root of -1, we can say the result is not a number, and that's got a certain exponent and fraction and so on. And we have some denormalized floating points where we can also represent things that are at one extreme or the other of the range that we can represent. So read through that, look at some of these examples, and we'll get some practice in class at the board.